video will focus on our last few concepts for this unit. We'll talk about ideal versus real gases, and then the difference between effusion and diffusion. So all of the mathematical equations that we've been dealing with in this unit have been for what's called ideal gases, right? And ideal gases, if you remember back to the kinetic molecular theory, are gases that hit with elastic collisions, so they can transfer energy but they don't lose energy. They have no force of attraction between adjacent particles, and they have no volume. Well, in reality, gases, right, all the gases around you, they have volume, and they have intermolecular forces. Otherwise, gases could never transition to become a liquid or a solid. So this law that we've been talking about, this ideal gas law, is under the stipulation that the gases that follow this relationship, right, again, have no volume, have completely elastic collisions, and have no IMFs. The truth is, there is a mathematical expression that relates pressure, volume, temperature, and number of moles for real gases, but the slight variation in the change barely affects the math in terms of the numeric value when we're dealing with gases under normal conditions. And the math becomes a little bit more cumbersome when you take into account the fact that real gases have volume and real gases have IMF, so we just ignore it. But today's conversation is for you to understand what happens when gases act like real gases. How does that affect things? So our ideal gas law only works well when we are at a low pressure system and a high temperature system. When I'm saying low pressure, I mean sea level, right? Even 1 atm is not considered that great a pressure on gases. High temperature, again, even room state condition is pretty high temperature for most gases. So we are dealing with ideal gases all around us at all times. The deviation from ideal happens when we have a high pressure scenario or a low temperature scenario. So high pressure scenario, we all of a sudden have the fact that we're forcing them close to one another. The volume of the particles starts to take a role, and so does the intermolecular forces, because they're close to each other often enough to make them potentially stick. And at a very low temperature, they have a low enough kinetic energy that, again, they start to stick to one another. So because of their volume and their sticky quality, when we increase the pressure very great, so push them really close together, or decrease the temperature a lot, all of a sudden they don't act like ideal, they start to act like real gases. So for our high pressure scenario, again, we find when we take a gas and start to apply a lot of pressure on it, at the beginning, under high pressure, you find that a real gas starts to have a smaller volume than you predict, and that's because the intermolecular force of attraction is drawing the particles closer to one another than they would if there were no force of attraction. And then as you continue to apply more pressure to them, eventually the volume is bigger than expected because the actual volume of the gas starts to push back. So if you look at the graph on the screen, you see the increase in pressure there, talking hundreds of atm, right? Not a measly 1, which is what we're at. And as you increase it, you'll see most of these graphs are going down from where we expect them to be if they were ideal, which is that horizontal line. And then eventually they go up. So they go down at the beginning because they actually are being pulled closer together because of IMFs. And eventually they go up from what we expect because they're pushing back against each other. One thing to note as you look at this graph is that the size of the atom is playing a role. Okay? When you have high pressure, stronger IMFs or bigger atoms are going to act less like ideal gases. So things that have stronger IMFs, things that can hydrogen bond or have a very, well, so most of these gases actually are nonpolar. So it's the bigger atoms that have the greatest London dispersion forces that are going to act the least like an ideal gas. So as we end up with really big molecules, that's where we get even more skewing than we'd expect. So if you look at this graph at the top again, carbon dioxide skews the most because it's the heaviest of all the other gases that are listed there, right? Methane and hydrogen and things like that. If we talk about the low temperature one, right, the very small kinetic energy, again, we talked about how moving very slowly, they'll just start to stick from one another. And so then again, you can see from this graph, as you go from hot temperature, about 1,000, it's trending kind of similar to where the ideal gas is. And as you get hotter and hotter and hotter, it's skewing more and more off that line. The other two concepts we're going to finish this unit with are diffusion and effusion. So diffusion and effusion are both the idea of gases moving. So again, that classic, if I have a perfume bottle in my hand and open it, and those gas particles eventually spread so you can smell them, that is diffusion. So diffusion is when you have particles that travel from an area where the gases are very highly concentrated to an area where they're low concentration. If you look at the picture on this screen, something that should probably come to mind with a lot of you is osmosis. Because osmosis is when you have something traveling across the membrane from high concentration to low concentration. It's exactly what diffusion is also. You're going from a very concentrated area of gases, and they're going to disperse through the process of diffusion until it's more evenly distributed, so from high to low. Effusion is the same idea, but instead of moving from high concentration to low concentration, it's high pressure to low pressure. So when you puncture a tire, or I'll show you guys a clip of the Metrodome tomorrow, if you guys remember ever going out the doors of the Metrodome, if you got to experience that, you have the push of gases actually going and flowing from an area of very high pressure gases to lower pressure gases. Okay, so that's the process of effusion. Effusion and diffusion are both things that you can calculate. So there is a relationship called Graham's law that we're going to talk about in class tomorrow. But I thought I'd give you a chance to write the equation down if you want to, so we don't have to spend as much time on notes for this. So Graham's law has a relationship with how fast the molecules are moving versus their molar mass, whether they're effusing or diffusing. So based on this, we can predict a certain amount of information about how gases are going to move based on the relationship of their equation. That's it. That's the last of the content. Now we have to apply this more in class, so make sure you just get the major concepts down from this video, and we'll take it one step further tomorrow in class. So go ahead and do the form, and have a nice night.